All right, so we're going to finish yesterday's lecture, and where we left off was this. We went through all of backpropagation, and then we mentioned that backpropagation, in fact, the entire computation of neural networks is probably best done using the vector formulation. And so the way we did the vector formulation was this. If I have a network of this kind where I have in any given layer, I have this thing is not aligned. The neurons of the previous layer, which are giving me, yk minus 1 superscript I. So I can arrange all of these guys into a vector. So I can say this is going to be y1 of k minus 1, y2 of k minus 1, and so on. And then this I can say is my vector yk minus 1, which represents the outputs of the neurons in the previous layer. And so then for the next layer, I would have a bunch of neurons of this kind. And at the next layer, obviously, what you're going to be computing is z1, k, z2, k, and so on. And these I can write as this vector z sub k equals z1, k, z2, k, and so on. So once I write these, then the things that I have to describe are these weights, right? And so we know that this term over here can be obtained from all of these guys and a set of weights. So we can say Z1, I'm skipping the superscript for now, is going to be W11, W21, and so on, times Y1, Y2, and so on, right? And so also we can write plus, of course. There's a B1 here. And then similarly, I can write Z2 equals W12, W22, and so on, times all of these guys. So when I write the entire thing down, I end up with this vector formulation, which says ZK equals WK, which is the weight matrix for the kth layer, times YK minus 1 plus BK. So do you remember this, all of you? Yes or no? Hello, anybody here? Yeah, okay. And so we ended up with this very nice vector formulation, which said that we can just write out all of the variables in vector format. The matrix of weights, all the weights can be arranged as a matrix where the first row of the weights matrix represents all of the weights to the first neuron at the output. The second row represents a set of weights to the second neuron, and so on. We can arrange the biases as a vector where the first component is the bias to the first neuron. The second component is the bias to the second neuron, and so on. And then once we write things in this manner, we can just say ZK equals WK YK minus 1 plus BK. So it's a very simple affine function. And then, of course, the output of the kth layer is simply the activation of the kth layer applied to ZK. So given this, now the entire forward computation can be written in this manner, that you just apply the affine computation. We can set the input to Y0 or Y0 to be the input. Then at the first layer, the affine term is computed using the simple affine formula, where the weights matrix are the weights of the first layer and the bias vector are represent the biases of the first layer. And then you can apply the activation of the first layer on Z1 to get the output of the first layer. And then subsequently, you can get the affine vector Z2 at the second layer simply by using this simple affine formula just as before, where y1 is multiplied by the weight matrix of the second layer, and then you add in the bias vector of the second layer. So that's giving you the affine vector at the second layer. And from that, now you can compute the output of the second layer simply by applying the activation of the second layer, and so on all the way to the end. And so the entire forward pass could be written like so. You set the 0th layer value to just be the input. Then you go forward through the layers, and at each layer, first you compute the affine value zk, which is simply an affine function of the output of the previous layer, where the affine weights are the affine multiplier are the weights of the kth layer, and this affine bias are the biases of the kth layer. And then once you've computed the affine vector, you can just apply the activation functions of the kth layer to it, and then you get the output of the kth layer. So a simple iteration over these two steps will take you forward through the network all the way to the end of the network. So this was this clear to everybody? Just give me a
yes
raised hands so I can count the number of hands raised. I have 35 people online, so this is going to get challenging from here. So anytime I ask you if it is clear to you, please give me a hands raised symbol, okay? And so this was the forward pass. You set y0 to the input, and then you iterate through the layers. And then at each layer, first you compute this affine value z through this affine transform, where the multiplier is the matrix of weights for the kth layer, and this bias is the set of biases for the kth layer. And then once you compute the affine vector, you apply the activation function of the layer to it to get the output of the kth layer. And the output of the final layer, of course, is the output of the network. So far, so good, right? So now we have to work with a backward pass. Now, when you begin talking about the backward pass, we have to deal with derivatives. And so now we have to worry about what do derivatives look like. Now, anytime you have a function of this kind where, let me see if I can. Please go away. So anytime you have a function of this kind where you have, say, y equals some function of, let me call this a, okay? So I'm having trouble aligning my pen to the screen. So suppose anytime you have a function of this kind, y equals f of a, where y is a scalar and a is either a vector or a matrix, then the derivative of y with respect to a, what will its shape be? Anyone? Same as a? Anybody else? What will the shape be? So when a was a column vector, what was the derivative of y with respect to a? What was the shape? Row vector, right? Okay, so now if you generalize this, what do you think the shape of the derivative of y with respect to a must be? Transpose of a, right? This is going to look like a transpose. So keep this in mind. We are going to use this. Everyone get this? This is regardless of whether A is a vector or a matrix. In fact, it also carries to tensors. That clear to everybody? Just give me a hands raised, guys. I don't see any hands raised. Okay, I need to see a few. Thank you. So, all right. Now we're going to start off with some pretty horrible vector calculus. If I have a vector function y equals f of z, okay? And z is a vector and y is a scalar, then here's how we defined derivatives, right? The derivative of y with respect to z is, which I've represented using this nabla term over here, is the multiplier that multiplies delta z, a small increment in z, to give you a corresponding increment in y. Now, if z is a column vector, what's delta z? If z is a column vector, what's delta z, guys? Column vector of the same size as z, right? And if y is a scalar, what is delta y? A scalar. And so if I'm multiplying a column vector by something to get a scalar, what will this term be? It's going to be a row vector of the same length as z, right? So it's going to be the dimensionality of the transpose of z. Now, we have seen this magical term called the gradient. When I have a function of this kind, then the gradient of y with respect to a will be the same shape as a. The gradient is different from the derivative. The gradient is defined as the transpose of the derivative. The gradient lives in the same space as a. Is that clear? And so over here, this term, the transpose of the derivative of y with respect to z, is called the gradient of y with respect to z. Now, so we're clear about this so far, right? Why did we choose to make it a row vector? Where did that convention come from? So to understand, now suppose I gave you a set of functions. I say y1 equals some function of a vector x. y2 equals some other function of a vector of the same vector x. y3 equals some other function of the same vector x. Then what is the derivative of y with respect to x? That's going to be x is a column vector, right? So what will the derivative of y with respect to y1 with respect to x be? Again, what's the derivative of y1 with respect to x? What's the shape? A row vector, right? So correspondingly, this is going to be a row vector. This is going to be a row vector. This is going to be a row vector, right? Now I can write all of these as a single vector equation, like so. I can say, y1, y2, y3 simply by stacking the y's on top of one another. There's f, where this f is a function which is also a stacking of f1, f2, and f3 of x, right? So if I write this, then clearly the derivative of y, so let me call this vector y, okay? Then the derivative of y with respect to x is also going to be a stacking, because this, all I've done is physically stacked a bunch of equations together, right? So the derivative of y with respect to x is also going to be a stacking of y1 with respect to x, y2 with respect to x, y3 with respect to x. This making sense, guys? Right? And so you can see now that, remember, earlier we had that delta y1 equals the derivative of y1 with respect to x times delta x, right? Similarly, delta y2 was the derivative of x with respect to y2 times delta x. So using this, so let me call this matrix J of y with respect to x, which is just the vertical stacking of all of these, the derivatives of the individual y's. And you can see that, just by comparing these, you can see that delta y, which is just a vertical stacking of all of these guys, is j of y with respect to x times delta x. Do you see this? Right? Which satisfies our derivative equation. This guy is called the Jacobian of y with respect to x. And the Jacobian also satisfies the derivative rule that we spoke of earlier. Everybody clear? Any questions? If you got this, raise your hands. If you got everything I've said so far. I'll wait till I see at least a dozen hands raised. Thank you. So, and you can see why this is so. So this notice, this is just reiterating this. My vector y is a vertical stacking of these individual y's. And so the derivative of y with respect to z is a vertical stacking of the derivatives of these individual y's with respect to z. And those derivatives are row vectors. So the Jacobian is a matrix of partial derivatives, where the first row is the row of partial derivatives of y1 with respect to the components of z, which is basically saying that the first row is the derivative of y1 with respect to z. And in general, the kth row is going to be the row of partial derivatives of yk with respect to the components of z. So this is your Jacobian. And again, you can verify that delta y is going to be the Jacobian times delta z, right? Again, observe that I've sort of changed the notation a little bit. I've put the y in the subscript and the z in the parentheses, unlike what I wrote on the screen. And that is simply to indicate that this derivative is actually a function of z. It depends on where it is computed. So, you with me so far? Please respond, guys, if you're with me, because if I've lost you, then I will have to repeat things. So may I see a dozen hands raised at least? Thank you. Now the Jacobians describe the derivatives of neural activations with respect to their input. If I have a layer which has many scalar activations, this is basically a vector activation where individual inputs do not only affect a single output, right? And so when you have a layer with activations of this kind, then the Jacobian is going to be a diagonal matrix where the diagonal entries are the derivatives of these individual activations. And the off-diagonal entries are all 0 because perturbing any input does not perturb the other outputs. On the other hand, if you have a full vector activation, then the Jacobian is going to be a full matrix where the ijth entry of the matrix is going to be the partial derivative of the ith output with respect to the jth input. So are these two things clear? All right. So this is easy enough, okay? Now let's begin talking about derivatives again, right? Suppose I give you, now I'm speaking entirely in terms of vectors. Suppose I give you z equals wy plus b. Z is a vector, y is a vector, w is a matrix, b is a vector, okay? What will, if I want to find the relationship between a small perturbation of y and a small perturbation of z, what is the relationship? Anyone? What is the relationship? This is just w, correct? And so what is the derivative of z with respect to y? Over here, what is the derivative of z with respect to y? Inspecting this equation. What is the Jacobian of y with respect to z? This is going to be W. Everyone with me? Raise your hands if you're with me. I'm going to ask you to do this repeatedly, right? Similarly, what is the Jacobian of y with respect to, actually, this is the Jacobian of z with respect to y, I'm sorry, right? So what is the Jacobian of z with respect to b? What is this going to be? This is going to be an identity matrix, right? Delta B equals delta Z times something. This has got to be an identity matrix, right? Everyone with me? Okay. So coming back here, if I have now Z equals WY plus B is basically the affine relationship between the output of one layer of the network and the input of the affine value of the next layer of the network, right? So in this case, I'm going to say Z equals WY plus B. So the derivative of the Z with respect to Y is just going to be the weight matrix. And the derivative of the Z with respect to, right, B is also going to be, and there are two other terms. We have to wonder about what the derivative of Z with respect to W and what the derivative of Z with respect to B are, but let's hold off on that. Now, so remember how we drew influence diagrams. Those influence diagrams also hold for the case of vectors. So, for example, if I write X influences Y, this is a generic thing. So if X is a scalar and Y is a scalar, what is the edge of this? What is the weight of this edge going to be? Anyone? It's just going to be dy over dx, right? If X is a vector and Y is a scalar, what is the weight of this guy going to be? What will this be? Y is a scalar, X is a vector. This is simply going to be nabla Y with respect to X, correct? Everyone with me? Okay. And if X is a vector and Y is a vector, what is this guy going to be? The Jacobian of Y with respect to X. But I'll generally represent this as simply using this nabla notation just for simplicity. So we agree on this, okay? Now let me try using the chain rule. If I've got some chained dependency of this kind, where X affects whatever Y affects Z, okay? So this guy is going to be, the edge or the weight of this one is going to be the derivative of Y with respect to X. The weight of this one is going to be the derivative of Z with respect to Y, right? What is the derivative of Z with respect to X? Can anyone tell me? What is the derivative of Z with respect to X? Multiply them how? Multiply them how? Is there an order? Or can I multiply them in any order? So you can't write this as dz over dy because they're not necessarily scalars, right? This representation, so this is going to, that's an nabla, but we know that delta y equals nabla yx times delta x, right? And we know that delta z equals nabla z y times delta y. which is going to be nabla zy times nabla yx times delta x, right? So this is the derivative of z with respect to x. Observe the order. The rightmost term is going to be the first term, right? So as you go, as you keep going outwards, you keep left multiplying. Is this making sense? There is an order to it. And what you will find is that so long as you maintain this order, all of the dimensions are going to match. So if I have something of this kind where x is a vector which affects y is a vector which affects z is a vector, okay, then the z with respect to x is going to be what? The derivative of y with respect to x times the derivative of z with respect to y. Both of these are going to be. So what are these? This is going to be a matrix and this is going to be a matrix. Each of these is going to be a matrix, correct? And the sizes will match. You can make sure that you can verify that the sizes will match. Now, on the other hand, so these are both Jacobians. If x is a vector and y is a vector and z is a scalar, then the derivative of z with respect to x has got to be a vector, correct? But this is going to be the derivative of z with respect to y, which will be a row vector, times the derivative of y with respect to x, which is going to be a matrix. And so a row vector times a matrix will give you a row vector, which is correct. Is making sense? If you got this, raise your hands, please. So anytime you're dealing with derivatives of this kind, it makes sense for you to actually write out the influence pictures and then write out the formulae, and you're certain to get all the dimensions just right. And so again, if I have just, these slides are just sort of reiterating this. If I have y equals y of z, some function y of some function z of x, then when you compute the derivative of y with respect to x, this is the first link in the chain. The outer one is the second link in the chain. So the outer one goes rightmost, and then the inner one comes to the left of it. Because this one basically says x influences z influences y. So using this logic, if x influences here, I have it in a different order. If x influences y influences z, then in the derivative, this term comes first and this term comes second. And so you will see over here that this guy is the first link, it comes second. The outer one is the second link, it comes first. This making sense? And of course, I've shown why the math works out. Delta y is, nabla y z times delta z is nabla zx times delta x. So chaining it all together, you find that the derivative is nabla y z times nabla zx, okay? So do you think you guys can actually remember, you may not remember the order, but do you think you can, based on this, you can work out the order on your own the next time you encounter this? Right. So over here, this should be, I'm speaking of delta y as a function of delta x. So in general, as you go into the equation, each term on the inside keeps appearing to the right. So if I write a nested equation, the first term is going to be the derivative of the first guy. the second term is going to be the derivative of the second guy, and so on. As I go into the equation, the inner derivatives keep multiplying to the right. So this is something worth noting, that if I generally have a function of this kind, which says y equals f1 of f2 of f3 of f4 of f5 of x, then the derivative of y with respect to x is going to start off with the derivative of y with respect to f1, the outermost, times the derivative of f1 with respect to f2, times the derivative of f2 with respect to f3, and so on. So as you go into the function, the inner derivatives keep multiplying right. Right, multiply. And you can see why the logic works. So is this making sense? Are you guys with me? I know this is annoying that I keep asking this question, but I have to make sure you're with me. I'd like to see a dozen hands raised. Thank you. Okay. And so, you know, this holds regardless of whether it's a vector function of scalars or a scalar function of vectors. The rule always holds and the sizes will match. That's what the next two slides are saying. And now, there's a final bit, right? If I have z equals wy plus b, and some z is a vector, y is a vector, w is a matrix, and b is a vector, and then I have some scalar d is f of z, right? Then what is the derivative of d with respect to y? So let me just write this down and I'll let you guys work it out. So I want to have, let me just think. Okay. So I have d equals some f of z, and z is a vector, z equals wy plus b, okay? I want the derivative of d with respect to y. What's this going to be? Can anybody tell me? Yes, but what will the formula be? Anyone? It's a vector. So if y is a column vector, you know this has got to be a row vector, right? But what will the formula be? Okay, let me write the derivative of d with respect to z in this manner, right? And then what next? Times w, correct? Thank you. So this is easy. And what is the derivative of d with respect to b? Anyone? I'm speaking of the derivative of d with respect to b. What's that going to be? It's going to be nabla dz times identity, which is nabla dz. Right? Guys with me? Perfect. So if you're with me, just raise your hands. I want to see this. We're going to use this all over the place. So I'd like to see more than a dozen hands raised. Okay. That's it. Only 13 of you. What about the rest of you guys? You get it? All right, thank you. So now here's the final bit. So this is the key piece. I have d equals f of z, and I have z equals wy plus b, okay? Now this, I'm not going to ask you to give me the formula for this because it's somewhat counterintuitive. But offline, maybe on Piazza, I can show you how this actually falls into the standard paradigm. But remember, earlier when I had f1 of f2 of x, then the derivative always went, the derivative of d with respect to f1 times the derivative of f1 with respect to f2. You kept right multiplying, right? But in this case, because W is a matrix, this only holds where everything's a vector or a scalar. But because W is a matrix, you get a strange inversion. The derivative of D with respect to W is actually going to be Y times the derivative of D with respect to Z. Observe that the outer one actually came to the right and Y came to the left. So this is in a different order than this one. Do you see that the order is different? Can you see that the order is different? Over here, right? What happened? D equals, right? So over here, you had the derivative of D with respect to F1 first, and then the derivative of F1 with respect to F2 first, second. Here, when I go from these equations, I get the derivative of D with respect to Z second, and Y comes first. So the order is inverted. Please confirm that you see this thing happening here. Okay, it seems kind of counterintuitive, but then suppose D is a scalar, 1 cross 1, right? Equals f of z, and say, well, let z is 1 cross n. And then suppose I say z equals w cross y, where y is, actually z is n cross 1, and say y is some m cross 1. What is the size of w? What is the size of w? N cross m, right? And what is the size of the derivative of d with respect to w? What should it be? W is n cross m. What is the derivative of d with respect to w? The transpose, right? This is going to be m cross n, correct? Let's verify that that holds for this term. What is the size of y again? What was the size of y? M cross 1. And what was the size of the derivative of d with respect to z? Where z was, an n cross 1 vector, or n cross 1, right? 1 cross n. And so what is the size of this product? What is the size of an m cross 1? Voila, you got the correct size, right? So do you see how the size works out when you have this equation? Can you see that the size works out? I'd like to see a few more confirmations. Okay. So how does this relate to our problem? Suppose I have a layer whose output is y, and let's say this is a n cross 1 vector, and then y goes through a matrix W, and so this goes into the next layer to produce a z, which is m cross 1. Then what is the size of W going to be? This is a layer, this is the next layer. What's the size of W? M cross n, right? Because n inputs and m outputs, right? And so now all of these z's eventually influence your divergence for the layer when you're training, where the divergence is a scalar. So therefore, if I take the derivative of the divergence with respect to this W, what we will find is that what is the formula now? What is the derivative of the divergence with respect to W using the form of what we just saw? Anyone? Using the formula y times the derivative of the divergence with respect to z. Is this making sense? Everyone? Please raise your hands if you got this. A dozen hands, please, please. Otherwise, I'll go over it again and can get, okay. Thank you. So that's where these two formulae came from. The derivative of d with respect to b is simply going to be the derivative of d with respect to z, because z is identically related to b, right? But the derivative of d with respect to w is the derivative of d with respect is y times the derivative of d with respect to z. So going back to our formula figure here, if I have a layer of this kind, if I have a network of this kind where I have some neurons and they're all connected to neurons in the next layer. So this is z here, y here, w here. And these eventually give you the output of the network from which the divergence is computed. Then the derivative of the divergence with respect to w is going to be y times, so the input of the layer times the derivative of the divergence with respect to the output of the layer. So again, in a situation like this, the derivative of the divergence with respect to w is going to be the input times the derivative of the divergence with respect to the output. Okay, so just remember this. And once we have all of these figured out, then the rest is straightforward. So that's basically what we're saying over here. If I have a layer of this kind, then the k-1th layer, the output of the k-1th layer is used to compute the affine value at the kth layer. And these affine values all influence the divergence. So the derivative of the divergence with respect to bk is simply going to be the derivative of the divergence with respect to zk. And the derivative of the divergence with respect to, the derivative of the divergence with respect to yk-1 is going to be the derivative of the divergence with respect to zk times the derivative of zk with respect to yk-1. So the derivative of the divergence with respect to this vector is going to be the derivative of the divergence with respect to zk times wk. And secondly, the derivative, so this is with respect to the input and output of the layer. These are all vectors. So here the normal rules apply. The derivative of d with respect to this guy is the derivative of d with respect to this term times the weight matrix. On the other hand, the derivative of the divergence with respect to bk is simply the derivative of the divergence with respect to zk times, and the derivative of the divergence with respect to w is y times the derivative of the divergence with respect to z. So this bit, all my fast speaking might have confused you, but are these two sets of equations? Do you see the distinction? And do you see that these are right? Any questions about these two guys? Because in the next 5 minutes, I'm going to fly through the rest of the slides. Right. So questions? Ari, is this making sense?
Yes.
Vegan, Divya, questions? Okay. All right. So there are two different situations. Thank you, Harshit. So I went through this. I'm having a little trouble with my pen here because the pen is misaligned with my screen for some reason. But so when I have a layer of this kind, which is y, I'm leaving the subscripts behind, and this layer is used to compute z, right? And then this z goes downstream and eventually is used to compute the divergence D. So I have Z equals WY plus B, and I have the divergence is some function of Z, right? So then if I want to compute the derivative of the divergence with respect to this vector Y, in between are the parameters W and B, right? If I want to compute the derivative of the divergence with respect to this vector Y, that is going to be simply the derivative of the divergence with respect to Z times the derivative of Z with respect to Y, which is going to be the derivative of the divergence with respect to Z times W. So Harshit, is this making sense? Okay, that was this slide over here. The derivative of the divergence with respect to Yk minus 1 is the derivative of the divergence with respect to Zk times Wk. So is this clear?
Yeah.
Okay. Now the next slide has to do with the derivative of the divergence with respect to these parameters. Let me change the color just to get the point across. So now we're speaking of the derivative with respect to these parameters, okay? And for that, we're going to have a slightly different equation. Can I shrink this? Okay. The derivative of the divergence with respect to B is simply going to be the because of, Z is identically related to B, right? So we get the derivative of the divergence with respect to B equals the derivative of the divergence with respect to Z. Harshit, is that making sense?
Yes.
Okay. And then there was the final bit. If I want the derivative of the divergence with respect to W, that was simply Y times the derivative of the divergence with respect to Z. That's what we had explained earlier. And that it will give.
Yeah, got it. Thank you.
Right? So these are all simple rules. We're going to apply them all repeatedly. Now, I'll skip the poll. If I'd done this in class, we would have had the poll. Actually, yeah. Can you answer this? You're given a function f of g of h of x, where x and y are vectors, and g and h also compute vectors. What is the correct formula for the derivative of y with respect to x? Can you tell me of these two? It's the second one, right? Going outwards in. Beautiful. You guys got it. Nailed it. So now let's go back to the backward pass. We're just going to use the formula we discussed in painful detail. And we'll just write up the backward pass in a minute. Here's how it goes. The first thing, in the forward pass, you computed all of these intermediate values, and then you got the desired output and computed the divergence, which is a scalar. The first thing you assume is that you can compute the derivative of the divergence with respect to the output of the network, which may be a vector. So this is going to be a row vector, right? This is easy. Again, remember the gradient is the transpose of the derivative. Everyone with me so far? This is trivial. This is nothing new, right? Okay. What do you think you're going to do next? Help me here. So let's say that this one is some activation function, and there's a z vector going into this activation function. What is the next thing you'd compute? Anyone?
Derivatives of activation function, I think.
So the derivative of the divergence with respect to z, right? And what is that going to be?
Derivatives of activation function multiply.
What is the order? So you want to compute the derivative of the divergence with respect to z, right? And using the chain rule, right? The outermost function was the divergence. So the first term is the derivative of the divergence with respect to y, right? And then you right multiply the derivative of y with respect to z. This clear? Right? And what is this guy? We've already got this term. What is this new term? Anyone? What is that new term? That's just the Jacobian of the activation. The activation got a vector input and a vector output. So it's the Jacobian of the activation. Right? If you're with me, just give me a thumbs up or raise your hands. Okay. 11. Okay. I'd like to see if more than a dozen. We have 35 people here. Okay, so what do you think the next term you're going to compute is? The derivative of the divergence with respect to this y, right? All the way back here. And the derivative of the divergence with respect to y, I'm just using the right multiplication rule, is going to be the derivative of the divergence with respect to z times the derivative of z with respect to y. Of these two terms, have we already computed any term so far? So again, the first term. And what is the second term? Weight matrix. So there you go, right? So the derivative of the divergence with respect to this y is the derivative of the divergence with respect to z times the weight matrix, the right multiplying the weight matrix. And again, this derivative was a row vector. When you right multiplied it by a Jacobian, you got a row vector. When you right multiplied by that by a matrix, right multiplying a row vector by a matrix gives you a row vector, so all the dimensions match, right? So if you're with me, give me a thumbs up or a raised hands. Okay. But now we also need to compute the derivative of the divergence with respect to the bias of this layer. What is the derivative of the divergence with respect to Bn? Anyone? What is nabla with respect to Bn? That's simply going to be this guy. The derivative of the divergence with respect to Bn is simply going to be the derivative of the divergence with respect to Zn, right? What is the derivative of the divergence with respect to W? Fantastic, you guys nailed it, right? So there you go. So now the derivative of the divergence with respect to W is going to be yn minus 1 times the derivative of the divergence with respect to Zn. And the derivative of the divergence with respect to Bn is that simply the derivative of the divergence with respect to Zn. And so we've got all the derivatives going back here. So everyone with me? What's the next thing you're going to compute? And what will the formula be? What is the next thing we will compute? Digant.
Like the derivative of the divergence with the input to the neurons, like I think z n
minus 1. And what is the formula for that?
So that would be like the derivative of the divergence with respect to the activation function. Wait, just a minute. So y would be f of c.
This is going to be the derivative of the divergence with respect to yn minus 1 times the derivative of yn minus 1 with respect to zn minus 1, correct?
Right.
And what is the first term has already been computed, right?
Yeah.
So what is the second term?
So yeah, that would be the derivative of the divergence with respect to the activation function.
No, so what is the second term?
So y is equal to like the activation function of z, so that would be the derivative of y with respect to the activation function. Wait, I think messing it up. I need to write it down.
Y is the output of the activation, z is the input to the activation, right? So it's the derivative of y with respect to z.
Y respect to z, right?
That's simply the Jacobian.
Yeah.
Correct? And so we worked our way all the way back to derivatives with respect to this term. What is the next thing we will compute? Anyone? Derivative with respect to yn minus 2, right? And the derivative with respect to yn minus 2 is simply going to be the derivative for zn minus 1 times the derivative of zn minus 1 with respect to yn minus 2. And of which this first term has already been computed. And what is the second term?
W.
It's going to be the W for the layer. Beautiful. And what about the derivatives with respect? Now we need the derivatives with respect to these parameters. And what will they be? The derivative with respect to this B is simply the derivative with respect to Z. And the derivative with respect to this W is going to be the Y over here times the derivative with respect to the Z, right? So this was what we had discussed over here, right? Abhishek?
Yeah, I just don't understand. Can you explain again why y comes first?
So I will not actually work out the arithmetic, but we can show that the size matches, right? So at least the necessary condition is satisfied. So I have y, and say y is, say, m cross 1, okay? And I have z, which is, say, n cross 1. So the weight matrix is going to be n cross m, correct?
Yeah.
Okay, so the derivative of the divergence with respect to W has to be, what will the size be?
M cross n.
M cross n, right? And so if I take y is m cross 1, and the derivative of the divergence with respect to z is 1 cross n. 1 cross n, right? And this gives you the correct size.
M cross n. Oh, okay.
Okay. Well, now the math is a little more involved how that formula actually happens. But if you take it for granted for now, then this works out, right? And then I can just keep following this rule, right? I can keep going backward and eventually using the same way, I'm going to compute the derivative with respect to eventually compute the derivative with respect to the affine value at the first layer, and then the parameters at the first layer of the first layer, and if necessary, even the derivative of the divergence with respect to the input. For the first layer, of course, derivative for W1 is the input x times the derivative with respect to z. So is the sequence, so the overall backward pass is going to look like this, right? You performed your forward pass and you got all the intermediate values. And then as a first step, you compute the derivative of the divergence with respect to the output of the network. Then you keep going backwards through the network. And so what you would compute is at each layer, the derivative of the divergence with respect to the input, the affine value at the layer is the derivative for the output of the activation, right multiplied by the Jacobian of the activation. And then the derivative with respect to the output of the previous layer is the derivative of for the affine value, right multiplied by the weight of the layer. So if you keep iterating through these two steps, we're going to get the derivatives with respect to all the z's and y's. At each time, you're taking the latest derivative computed and right multiplying it by a matrix. So here, you're taking the derivative for the y value for the layer and then right multiplying it by the Jacobian. Then here, you're taking the derivative which you just computed earlier and then right multiplying it by the weight matrix. Then you go back here, and then the derivative that you've just computed is right multiplied by the Jacobian, and that result is then right multiplied by the weight matrix. So as you keep going back through the network, you keep right multiplying terms. That making sense? Yes, no. Right. I'll wait for a few. We're almost done, but just I'd like to see a few more hands raised. $11. It's maxed out at 11. Okay. And intermediate in the middle, we are also computing derivatives for the weights and the biases for each layer. And the derivative for the bias is simply the derivative with respect to the affine value at the layer. And the derivative for the weights is simply the input to the layer times the derivatives with respect to the affine value. And so we have computed the derivatives with respect to all the parameters of the network. That's for a single instance. And so if you wanted to train a neural network where you've got a whole bunch of training instances, you'd initialize all the weights and biases of all the layers. Then you'd first, in the forward pass, you'd go through all of your training instances. In the forward pass, you're going to simply pass the data through the network using the formula we saw earlier and compute the output of the network. Then you compute the divergence for that instance. And then you sort of pass that instance backward through the network to compute the derivatives with respect to of the divergence with respect to all the network parameters using this simple recursion that we just saw. And then once you computed the derivatives for all of your training instances, the average of these derivatives is what you would use within your gradient descent step to update your parameters. And you keep doing this until the loss is converged. So questions, any doubts? All of this, everything here clear so far? Please, I'd like to see a few hands raised. Yes or no? All right, thank you. And so here's how you'd set up for to train the network. Let's say you're given a task of recognizing the digit 2. You'd have a collection of training instances, where each instance is the input, which might be an image, and a label, which in this case is going to be, is this an instance of the digit 2 or not? We'd set up the network, we'd define the divergence, and then you'd use the backpropagation algorithm that we have over here to compute all the derivatives. If you were performing multi-class classification, then the labels for the instances are going to be the actual, rather than binary labels, you'd assign the class label for each input, which in this digit recognition case is going to be the digit that the image represents. You'd set up the network. In this case, we're trying to recognize 10 classes. So the output layer could have either 10 outputs, one corresponding to each class, or even 11 outputs, where the 11th output is none of the above. And so the output layer of the network would be a softmax layer. The divergence should compute for each training instance is the Kullback-Leibler divergence. And then you'd use the backpropagation rules algorithm to compute the derivatives with respect to all parameters of the network. And so the story so far, neural nets must be trained to minimize the average divergence between the output of the network and the desired output over a set of training instances. Minimization is performed using gradient descent. Gradients of the divergence with respect to network parameters can be computed using backpropagation, which requires a forward pass of inference followed by a backward pass of gradient computation. And the computed gradients can be incorporated into gradient descent. There are some issues. So we've sort of seen how the entire training process can be set up. But there are some issues like, will it converge? How fast will it converge? And will the models that we have learned actually represent instances outside our training data? What does the output really mean? And so on. We'll deal with these in later classes. So I'll stop the recording right here.